Welcome to this seminar in the COVID-19 data science series. Today, we are fortunate to have Allocation, who was previously co-director of MIDAS, Dempsey, an assistant professor of biostatistics, and their student, Wang, who have who have jointly been working within the past few months on analyzing Twitter data and to find patterns in it of societal responses to this pandemic. I'm excited to hear what they found and what they did. And so without further ado, I'd like to turn it over to Walter and Wayne.
Thank you. I'll start sharing my screen.
I can just get started by saying a few words that sort of this grew out of the COVID-19 lockdown. In March 2020, of course, we were all homebound and in the midst of a very intense primary season. We had COVID-19, and we got together basically on the basis of an observation that the news media was reporting a lot of issues with testing capacity being limited, people being turned away from testing facilities, and the number of cases was rising. There was what was a palpable emerging panic with stockpiling of all kinds of toilet paper and hand soap, cold medications, and so forth. And so the questions that naturally arose was, is there a way to maybe get an alternative, not necessarily better, but an alternative understanding of the public discourse, the conversations, the discussions in the public discourse on these issues, the COVID-19, both in terms of policy, response to policy, health resources, and just anything else. And so, there were obviously, we have Twitter, and through MIDAS, we have 10% Decahose, which is a very valuable resource for getting at this sort of ground level sort of population distribution of opinion, anonymized for the most part, allowing us to perhaps ask or at least get some insight into questions of what topics are people really talking about? Does it lead the news or lag the news? Is it orthogonal to the news? Are there insights into the emergence, the evolution, and even extinction of different types of topics in the public conversation? And perhaps even there might be some way to quantify what we're seeing in these in this Twitter feed and the topics that are being discussed over time as they evolve, that could lead to a better understanding of public opinion and access to resources, effectiveness of policies, validation of news, and so forth. So the group, which consists of people from the School of Public Health, ISR, LSNA, College of Engineering, Medical School, we sort of put our minds together and said what we need is a tool. And unfortunately, there is no such tool that we know of for longitudinal, that is dynamic over time, topic analysis. There are lots of tools for topic modeling, pulling common topics from documents that are in the public domain, but that don't have the microtext and the the particular challenges that Twitter has. So what we did was we built a simple, interpretable, dynamical topic model to extract information from Twitter. It can be used for other types of social media or other types of problems that have this dynamic nature to them, social media in particular. And we use this to learn and visualize trajectories of topics that summarize the public discourse over both time and over space. I don't think we're going to show any results over space in this talk, but we've been looking also at sort of spatial distribution of different opinions and topics that appear. So it's the first tool for dynamic topic analysis using latent Dirichlet applications. It combines, you can go to that slide maybe, Wayne,
Yeah.
on the Venn diagram.
Yes. Yeah. Here it is.
I'm not seeing it.
Uh,
I'm not seeing, I'm viewing your screen, but it's just the first, just, is everyone else? Yeah, I'm just seeing the title slide.
Oh.
Same here. Wayne,
Let me see. Oh, can you see that now or?
Nope.
No, try restarting Zoom. I've seen this happen before.
Oh, yeah. Let me stop sharing and
Right.
do that again.
Okay, well, even without the Venn diagram, let me just say that, you know, this work would not have been possible, and certainly would have not come up together so quickly without a team of people that represent expertise in areas of statistics, computational geometry, algorithms, machine learning, and so forth. And I think that, you know, that's really a testament to what can be done under circumstances that aren't ideal if you bring the right interdisciplinary group together to work on both tools and interpretation and discussion of the needs in this particular Twitter interpretation problem.
Can
So
you guys see
Wayne,
the screen now? Or?
Yes. Yeah. Why don't you take it from here?
Okay, sure. Yeah. Thank you, Al. Thanks for the overview, and sorry about the slide sharing stuff. So my part of the talk is going to be guided by this roadmap, basically. So I will introduce a little bit more details about the Twitter data we use. And then I will talk about a set of tools, as Al mentioned, to help us describe and extract information from the Twitter data. In particular, I'm going to mention a tool called LDA, which is a very popular and widely used tool in natural language processing to extract information basically from these documents. That will get us this topic time matrix of word clouds that are very important to understanding the documents we have. And then I will introduce this notion of distances so that we can connect all the separate cells together to give us a understanding of what happens of the topic through time. And then I will also introduce these kind of tools from computational geometry to help us basically understand the natural progressive path from one topic to the other, and then visualize them in some space, some lower dimensional space that is easy for us to interpret. Okay, so that's the plan. I will go into the data. As I'll just mention, thanks to MIDAS, who made the Twitter deck host data stream available to us. So as stated on the Twitter website, this deck host stream will give us a 10% randomly selected sample from all tweets from a given day. So for a given day, they're estimated to be about 300 to 500 million tweets. And also, this enables us to do sort of spatial analysis of the tweeting behavior because this data set also gives us a reliable and diverse geographic location information for each for each tweets if the user decided to turn them on. So for this study, we are actually going to focus on a certain time period from February 15 to May 15 that we think, that we expect there to be a large volume of tweets about this COVID-19 topic. So if we look at the plot on the left, so which is a plot of number of tweets against time, as we can see, as promised by the deca host, we are getting about 30 to 50 millions of tweets per day, which is about 10%. And we are going to do some subsamplings and focus on that subsample tweets. In particular, we are going to limit ourselves to the tweets that are geotagged to the United States, as indicated by the geographical location by Twitter, so that we can study the spatial variations for this particular region. And also, we are only going to work with English tweets. English tweets here basically means the tweets from the user who actually set their default language to English. So that the result from the models I will talk about later will be easier for us to interpret. And also to study only the inference of the original tweets, we are going to eliminate all the retweets. Retweets here basically means people retweet some others tweets instead of creating their own. Again, this is indicated by one of the variables from Twitter. And the resulting subset is the plot. The volume looks like the plot on the right. So we have about 50 to 100,000 tweets per day for the time period we would like to focus on. Okay, so one question you may ask is that, is the subsample tweets okay for us to do analysis? So of course, we're aware of the limitations, and if you are interested in some general purpose statistical analysis using the data, of course, you would need the data, the subsample data, to be a representative sample of the whole population. But in this case, our interest is not doing predictions nor making strong inferential decisions based on the data. So the focus of this study is going to be on the public discourse around COVID-19, and these selection bias and noisy issues is not that severe for us. And we're just interested in understanding this particular subpopulation. Okay, so that's the data. Next, I will start to introduce the set of tools or methods that we use to describe the data. And the first set of tools that I'm going to introduce is a class of model called the topic models that we can use to extract information from the text, from the Twitter text. Okay, so I'm going to motivate this topic modeling approach using this excerpt of an article published on the Science Journal. So if we look at a document like this, and we can see that oftentimes the words can be grouped together into different categories or topics. So for example, if we look at the word highlighted by the yellow color, they are all forms of the word's genes. Okay, so if we look at the blue words, they are all about something about computer and numbers. And so if we go ahead and highlight all the words by different colors and to emphasize their categories or topics, we can probably explain the documents by this set of unobserved but actually existed topics or categories. So this method we use, called the latent directional allocation model, is actually motivated by the fact that documents actually exhibit multiple topics or categories. So the model goes like this. So if we assume there is indeed this underlying but unobserved generating mechanism for every word in a document, so when we writing or generating each word, we first look at this topic proportions and assignment, which basically give a weight for each topic in our list. weight is basically some probability. So let's say now the probability of the yellow words, the genetic words are higher. So that means for a given word, it's more likely for us to choose a word from this category. So once this topic assignment procedure has been done, we then look at the word distributions for a given topic. The word distribution is just a distribution over all possible words. Again, it's just given weights for each of the word. So if this probability of Jing is higher, that means it's more likely for us to draw a word Jing from this topic. Okay, so and this LDA model is basically a model that tries to learn the probability distributions, in particular this word distribution and this topic assignment distribution from the observation of this document. Okay, so here is just a more technical summary of what I have just talked about. So I won't go into details about it, but just mention that in order to apply the standard LDA methods to Twitter data, we have some issues. So tweets, or more generally the microtext kind of data, usually concentrate just on single topics. So we can have a very short sentence or very short tweets to be generated from many different topics. And also, since it's very short, we need some notion of aggregation and pooling of different sentences or tweets together in order to form a document in the traditional sense. So that's why we use this Twitter LDA tool. Basically, does these two modifications. So it aggregates all the tweets, for example, from a single user, and it does some regularization such that each tweet is constrained to be generated from only one topic, right? So, but further, as we just mentioned at the very beginning, we are interested in actually the time evolution of those topics learned from the model. So what can we do about that? So there are these dynamic topic models that discussed in the literature that takes this temporal evolution effects into account. So I will illustrate the idea using actually the results from such a model. So what's shown here is two topics generated from a dynamic topic model, which was actually fit to the Science Journal from 1880s to around 2000s. And what's shown here on the top row is the top words at each decade. And the middle row here is just a proportion of science articles that belongs to this topic. And the bottom row is the weights of different words. So what we can see or observe from this results of the dynamic topic model is that if we look at the top words, from time to time, they only differ by a small amount. So for example, from the first one, 1880 to 1890, it's just the different order in the first two words, and so on and so forth. So in other words, these word distributions or topics are going to be smooth over time. So basically the idea at a very high level of this dynamic topic model is trying to chain together the topic and the topic proportion distributions we just mentioned through some random walk stochastic processes model. And it fits this model jointly across all time points. So whether we can use that for Twitter data. So of course, there are advantages of this kind of models. So the dynamics, basically the time evolution, is explicitly built into the generative process, which is good. But there are also some disadvantages. So in particular, since we're assuming, since it's a model-based approach and we have to make assumptions about the data we have, that means this approach is going to be sensitive to those model assumptions. And also, since we're fitting jointly a stochastic process model, so computationally it could be very expensive. And oftentimes, people will rely on some sort of approximate inference algorithms to learn all the distributions. And also, very important, there are no widely acceptable existing softwares for these dynamic topic models aiming at this microtext or short documents, which is what we have. And our goal in this study is actually to provide a very simple suite of tools using generally available, robust, widely used softwares. So instead, what we're going to do is to mimic this idea of the dynamic topic models while taking a simpler and more interpretable approaches. So what we're going to do is we are going to emulate the true dynamic model by building the dynamics into the data. So I'll introduce this notion of temporally smooth corpus. So here I will just use a very simple example of 5 documents. Each just contains 5 tweets. So the document here means that, for example, doc 1 aggregates all tweets from day 1, and doc 2 aggregates tweets from day 2, and so on and so forth. So we have this 5 documents with 5 tweets in each of them. And what we're going to do is we're going to construct 5 different corpus, one at each time point. So at the first time point, we're going to subsample tweets from each document. So in this case, we're going to use all tweets from day 1, and we're going to use only 75% of tweets from day 2, from doc 2, where 0.75 here is a subsampling parameter that we choose, and so on and so forth. And for the second corpus, we're going to subsample the docs again using a different set of weights, but condition on what we already have from the first corpus. As an example, if we look at this doc 3, so we, according to the weight, we will have 4 tweets in this doc. But instead of just randomly sample 4 tweets from the entire document, we condition on what we have, which is tweet 134, and just sample 1 additional tweet from the remaining of the document. So in this, so by doing this, we will end up with different corpus that are smooth from time to time. And then we're going to apply our Twitter LDA model independently in parallel to each of those corpus we constructed for all the time points. And we assume that there are 50 topics in each of the corpus, basically. And what we'll get in the end will be marginal model fitted results instead of joint results in the originally proposed dynamic model. Okay, so now we have all those independent marginal results. So if you remember from the first plot, we have those arrows connecting up all these topics or word distributions. So how can we connect them, connect all those topics, basically? So again, the goal here is just to stitch together all the marginal LDA results by connecting all pairs of topics from any consecutive time points. And in addition to that, we are interested in assigning some notion of weights to each of those connections, such that we can measure similarities for any of those edges, and also for any particular path on the connected matrix or graph, we can have an understanding of the quality of that particular path according to this weights, okay? So the idea here is that we would like to have a measure of similarity between topics, but topics are just represented by distribution over words. So what we need essentially is a similarity measure between discrete probability distributions. And the property we need from this measure is very simple. So if 2 word distributions or topics, like the one on the top row, are very similar, in this case, they are all talking about coronavirus, we want the distance to be very small. And if they're not that similar, in this case, at the bottom row, we want the distance to be large. So the particular distance we're going to use is this Hallinger distance, which is a widely used distance measure between discrete probability distributions, and it can compute it simply by compute the Euclidean distance between the square root of the probabilities with some constant scaling factor. And this will give us a number between 0 to 1. And indeed, we have the properties we need. If two topics are very similar, like this one, it will give us a number that is small and close to 0. If they're not quite similar, like this one at the bottom, it will give us some number that is large and close to 1. Okay, so now we have a fully connected matrix or graphs, but it's not very useful to us yet. So what we will like is sort of an interpretable path between any two observations. In this case, two topics or word distributions we have. So what we are interested in obtaining is a picture like this on the right. So if we pick 2 points, like this one, at the beginning is a fist, and at the end is a relaxed sort of gesture. So if we think they are related somehow, and we pick them, and we sort of find a path of transformation between the beginning to the end of the observations, in this case, images, and we would like to get this naturally progressive path between them, right? So in this case, what it does is it uses notion of neighborhood graph and computed a shortest path on this graph as labeled by the red curve here that actually captures this perceptual and natural but highly complicated transformations that actually approximates the underlying true geodesic path as labeled by the blue curve here. So essentially what we need here is constructing a neighborhood graph instead of using the fully connected matrix or graph that we have at the beginning. So here's a little motivation using a classic synthetic data, the Swiss road data. So if we look at the picture on the left, if we just take 2 arbitrary points that we think they're correlated somehow and measure their distance as labeled by the dashed blue line here in this high dimensional input space. So this distance actually may not accurately reflect their intrinsic similarity, which is actually measured by the solid blue curve here on the lower dimensional manifold. So, but if we first construct a neighborhood graph like this one, as the points are connected using gray lines, what we will get is this nice red curve approximation to the true geodesic path. And it has been shown in this paper that if we have enough of these connected points, this approximation actually is going to converge to the true path. Okay, so that basically gives us the motivation to use a neighborhood graph and find the shortest distance, in our case, between the word distributions. So here is what it looks like in our data. Okay, so here we choose 2 topics, one at the beginning, which is this one, a general coronavirus kind of topics, and the other one on the far right here is the end topic, which is still a coronavirus, but more related to testing and maybe healthcare kind of topics. And we're interested in finding a trajectory between these 2 topics. So this is of interest because we want to understand how the conversation about coronavirus and healthcare change around this COVID-19 changed over time. And we want to do so by making very minimum assumptions. So showing here are shortest path computed on a fully connected graph and a neighborhood graph where we connect each node with its 10 nearest neighbors. So what we see here is that at the bottom, so they are connected and the distance are very small, but what it did is actually connect these two topics with some random sequence of topics that are similar to each other, but has nothing to do actually with coronavirus. So basically what that means is that the transition path we got here is not natural, it's not perceptual natural. But if we do it on the neighborhood graph, as we can see that it picked up this naturally progressive path from some coronavirus discussion to some very closely related to coronavirus discussion in the end to a more testing and healthcare focused discussion about the same topic. Okay. Right, so now we have the distances. We have connected up all the topics time by time. So what we need now is to sort of visualize these in some lower dimensional space that is very easy for us to interpret. And also we would like to, instead of just finding out one or two of the paths, we want to find more of those and sort of study the relationship between multiple shorted paths of topics of interest. So now I'm going to introduce this idea that helps us to achieve that. So again, the goal is to basically visualize and interpret high dimensional word distributions. In this case, the dimension of the word distribution is going to be the length of the words, the length of the number of the words, right? Which is in thousands dimensions. And we need some lower dimensional embedding that captures and preserves the intrinsic high dimensional trajectory structure of the data, since we're actually interested in temporal evolutions or temporal relationships in the data. So what kind of tools we have? We have traditional tools like PCA, but actually PCA is very restrictive. It assumes linearity in the underlying lower dimensional space. So some other non-linear methods like t-SNE, which does not assume linearity, but do not naturally capture this kind of trajectory or progressive path in the data. Okay, so the tool we're going to use is this tool called FATE, which is actually designed to explicitly preserve or capture the progression structure in the data. Okay, so I will introduce the method by using this synthetic example. So here, the graph on the right is for this synthetic or artificial tree data as the ground truth. So if we apply these three methods to do dimension reduction or clustering of the data set. So as we can see that PCA basically fails to even separate some of the branches or some of the clusters on the tree. And method like t-SNE will do a better job at separating all those branches, but it fails capturing some of the branching point or some of the splitting point on this tree, which is sometimes very useful for us to interpret the data structure. But if we apply this tool FATE, as we can see that all the branches of the tree are properly and accurately separated, and all the branching or splitting points are also got picked up by this method, right? So this FATE basically uses ideas from heat diffusion processes to first denoise the data and use tools from differential geometry to basically recover the underlying intrinsic geometry or progressive path that exists in the data without making any strong assumptions actually on the data. Okay, so now we have all the tools we need. So we have the data. We apply LDA on the temporally smooth corpus to get this topic by time matrix. And we have this notion of Hallinger distance so that we can connect them up with different weights. And also we have this neighborhood graph and shorted path tool to help us to find these natural progressive paths from topic to topics. And also we can visualize many of these paths on a lower dimensional fate embedding. So next I will present the results, basically application of these methods on the Twitter data to see whether I can give us some insights about COVID-19 discussions on Twitter. All right, so the first plot show here is the fate embedding and the whole procedure applied to the whole data set. So we have about 4,500 word distributions, and each of these dots on the plot is actually representing one of those word distributions. And I will mostly use this overall graph, overall embedding, to explain our labeling techniques, and then go into more gradually zoom in to the sub clusters and subpaths to explain it in more detail. So here, the different colors are actually to represent different clusters as computed by a simple hierarchical clustering algorithms. So here we only colored a selected set of COVID-19 related topics, and all other topics are grouped in this blue or purplish color. And also we indicated volumes, a normalized volume of tweets for each topic by using different sizes of the points. And also we labeled different shortest paths computed on the neighborhood graph using different shape of the points. Okay, so here is a subset of the data and a more zoomed in version for only the coronavirus related topics. So as we can see, as promised by fate, we already have some very interesting structures. For example, we have this straight line or linear kind of structure down below. And for at top, we have this sort of hook or a U-shaped structure here. And we have some branching structures like what has built into the fate embedding. So here, these blue or purplish clusters or paths are close to this other path at the beginning and separated out after some time points. So next, what I will do is I'm going to focus on two case studies, which are two particular paths or subset on this graph. In particular, I'm going to talk about this hook here, and I will focus on the square shaped points first. And then in the second case study, I will talk about this shape here, and I will actually lift this to 3D so that it's easier to see the structure. Okay, so the first case study is about topic that we call the presidential election topics. That is not that COVID related, but I will tell you that there is a COVID-19 story in this path actually. So the reason that we picked this path first is that at the beginning, it's not clear to us whether these COVID-19 related topics will get extracted and whether this kind of trajectories will picked up by our procedure. And we wanted to understand these trajectories by using some real events that we have a good understanding about. So the presidential election topics, we can easily find some news items or Wikipedia page online to correlate those events with this path. Okay, so what we have on the graph is, again, the subset and a zoom in of the hook or U-shaped kind of path. And I label the time points by different colors here. So the dark blue or purple means the starting of the time period, and yellow here is the end of the period, which is in late, which is in 15 of the May. And the volumes, again, are proportional. The sizes of the points are, again, proportional to the volume of the tweets. So as we can see that there are on this path some small clusters or groups of points. So for example, this one down below here are some points that are relatively high volume and clustered together. So as I labeled the time here, this set of topics is actually from the Super Tuesday week. And two typical topics in this cluster is represented here, as we can see that people are generally talking about a few famous politicians and basically their performance in the Super Tuesday week. So one other subcluster in this pass is this April, cluster from late March to April. So as we can see that after the Super Tuesday week, the volume of tweets in these topics actually almost dies out. The reason we think here is that because of the COVID-19 situation in the US get very serious and severe in mid-March. So that's the reason that people probably sort of forget about this kind of election topics and start to talk about the COVID-19 related topics. Okay, so in April, there is a small increase in terms of volume and clustering together. We think the reason is that on April 8th, Bernie Sanders actually dropped out the race of the presidential election campaign. And also Joe Biden actually won 2 of the Democratic primaries in late April. So that might be the reason that this small cluster and increase in volume happened. Also, some other interesting effect is that in mid-May, which is the end of this study period, we see that the topics, as indicated by the word distribution here, changed a little bit from election to a more general politics and related to coronavirus, and actually converged if we plot on the same graph another path in this cluster. It actually converged with some other topics that are COVID related. Okay, so that's the presidential election path. And I will talk about then the COVID topics that we extracted from the data. So I will first explain the 4 word clouds of word distributions on the right. So what we have here are 2 pairs of beginning and end topics on the shortest path. So if we look at the 2 topics on the top, so at the beginning is a general coronavirus topics, and in the end is a testing or healthcare related coronavirus topics again. And the other one, which is very similar at the beginning to the other topics, is about coronavirus, about people, about healthcare. But in the end, they actually converge to something similar in the presidential election kind of topics, is about politics, right? So, and this kind of bifurcation and divergence of conversation structure actually got picked up in the fit embedding on the left. So as we can see that the 2 different paths, as indicated by different shapes of points, are close to each other at the beginning, but after some point, they just diverge to different conversations, one about public health and the other about politics, right? So this kind of bifurcation structure is naturally picked up by this fit embedding R&R shortest path procedure, but it's actually very hard to build one of these structures into some model like the dynamic LDA or the standard LDA model. So this indicates actually the advantage of this kind of approach by looking for the shortest path and doing this fit embedding. Okay, so on this slide, what I'm about to show is the same topic. So this one, it's just a different view in 3D, and I'm actually going to show a movie that shows this kind of evolution or movement of topics on these 2 trajectories actually. So I highlighted this kind of evolution by yellow. So what we'll see is that the points, both the circle and the cross mark points are close together at the beginning of the time. And then they sort of move away from each other and diverge to their different subregions. Okay, so I will play the video. So they're close together and then goes into their own loops. And then at the very end, they are going to be ended up at very different regions on this 3D fate embeddings. So again, this bifurcation and temporal evolution structure is naturally picked up by this fate embedding technique. Okay, so here I will conclude the talk. So in this talk, we combine tools from statistics, computational geometry, and algorithms to provide efficient ways to understand the high-dimensional and noisy Twitter data, which give us some visualization and interpretation about the public discourse around COVID-19. And of course, the key feature is that we're able to do longitudinal analysis of Twitter data without any complicated stochastic model like in the dynamic LDA. And this, of course, helps us to understand the impact of COVID-19 on various aspects. And some work we're currently focusing on are wrapping all these different tools into a single reusable software for general use. And also we're interested in apply such tools to some other regions other than the United States and even globally for all the tweets. And also we're doing some, although I haven't talked about it, we're doing some spatial analysis using the geotag feature of the data we have. And that's it for the talk. Thank you.
Brilliant. Thank you so much, Wayne.
Yeah.
And we do have some time left here. So if anyone in the audience has any questions, please feel free to put that in to the Q&A or the chat window, or feel free to raise your hand if you'd prefer to have me unmute you and you can ask the question out loud and kind of turn it over to the team to let them answer anything.
I should add also that we do fully intend to release the software that led to this presentation, and we haven't released it yet. But if anyone's interested in applying this technique to their own types of data, just send us a note, and we'll put you on the mailing list when our software is ready.
Brilliant. Okay, not seeing any questions come through here, so we'll just kind of give it another minute or two, and otherwise maybe we can let people get back to their days a titch earlier. It's really cool that that software is going to be available, though, Al. Thanks for sharing that. All right, well, it doesn't look like any questions are coming through. So I guess I would just like to thank all of you for taking the time, Wayne for leading the presentation. All really fascinating, very interesting work. So again, thank you for the time, and I hope you all have a good rest of your day.
Yeah, thank you so much.
Thank you for the opportunity.
Yep, thank you.
All right, take care.
Okay, bye.